Hi. As I mentioned on Friday, I want to continue going through the chapter in the book about um, how evolution happens so that you are prepared um, with the same teaching that you would have gotten in like a AP Bio class, at least for this particular chapter. I don't think we're going to have time to go through all the chapters. I'm going to set my timer because I'm not supposed to go over 10 minutes on the videos, and we'll just get as far as we can. And your assignment, as I mentioned on Friday, is just to continue working on your On the Origin of Species chapter. So I'm trying to get my phone to not fall over. And chapter 7 through 10, I think it is, are all due on this Friday, 1 o'clock, and we'll have a discussion then. Okay, so let me find that PowerPoint. All right, so we've been going through, let's see if I can move this over. We've been going through the processes of evolutionary change, and the first one we went through was Darwin's idea, which of course he shared with Alfred Russel Wallace about natural selection. And I'm not going to go through all that again, especially because you're reading Darwin's book, but I just wanted to remind you that that was the first process of evolutionary change that your book addressed. And the second process of evolutionary change that your book is going to talk about is this idea of mutation. So how mutation generates genetic variation within populations. So yes, natural selection has its part in changing the genetic makeup of a population from one generation to the next. But those variations are generated by mutation. And of course, Darwin didn't know about mutations because he worked in the 1800s before we understood genes and how mutations were generated. So I'll just remind you that a mutation is any change in the nucleotide sequences of an organism's DNA. They occur randomly and with no respect to whether it's going to be beneficial or not. It's literally just a random change in the genetic makeup of an individual. Mutations can be helpful sometimes. More often they're harmful, and you can just look at a number of different diseases that have genetic causes to see that. And sometimes they're just neutral, so like they don't help or hurt the organism. The mutation rate in organisms is really low, and I have it listed there on the screen, but even the low rates can add up because the number of base pairs in an organism's normal genetic makeup of a particular cell is like in the billions. So even if the rate is very low, every time an organism makes a gamete, there's at least like in humans, then that gamete, the chances are it'll have like 3 new mutations that weren't corrected by proofreading or mismatch repair. Those mutations, as we talked about before, can result in different alleles. And remember that alleles are different forms of a gene that occur at a given locus. So, for example, at the locus for the gene for eye color, one allele might be brown eyes, one allele might be blue eyes. So we need to just stop and define a few terms here, because we're going to be throwing them around a little, and most of these we've talked about in the past with genetics, but just to remind you. So remember, as I just said, alleles are different forms of a gene that are found at the same locus. So for example, like if you're talking about blood types, there's 3 different possible alleles, A, B, and O. A locus is a specific location on the chromosome. A population is a group of individuals of a single species that live and breed in a particular geographic area at the same time. And you want to think about populations really important here, because the idea of evolution is the change in populations of organisms over time. When we're talking about grand scale evolution, we're talking about changes in populations over time. The gene pool is the sum of all the copies of all the alleles at a given locus found in a population. And within the gene pool, you can calculate the allele frequency, which is the proportion of each allele in the gene pool, or the genotype frequency, which is the proportion of each genotype among individuals. And the reason I bring that up is because that's scientists use allele frequency and genotype frequency, those measurements, to like chart, if you want to say, or like show that evolution is happening within a population, because if that population's gene pool shows changes in either allele frequency or genotype frequency over time, they would say that that population is evolving. All right, this just gives you an example of what we mean by allele frequency. So let's say that in a particular population of organisms, you had 30 different individuals. And in this diagram, each oval represents a single individual. And of course, each individual can only have 2 alleles for each trait, because they have pairs of chromosomes. We're talking about organisms that are diploid like us. So if you were talking about like the example of the blood type, you can have A and B, or 2 A's or 2 B's, or an A and a B, or an A and an O, or a B and an O, and 2 O's, but you can only have 2 of each one. No matter how many different alleles exist, each individual only has 2 alleles for each trait. So if you look at the gene pool for this locus, which they're calling locus X, then there's 60 total alleles in the population, because there's 2 alleles per individual, and there's 30 individuals. And if you looked at the allele frequency for X1, which are the green halves of the ovals, then there are 12 of those X1 alleles within the total of 60 different alleles within the population. So 12 divided by 60 is 0.2. And you do the same type of thing for X2 and X3. So like I said, if a scientist is studying how evolution occurs in a population over time, one of the things she would do is measure the allele frequency at some point in time, and then come back later and measure the allele frequency within that population again, and she would be able to see how the allele frequencies are changing. And let me just say that the idea is that the reason the allele frequencies would change is because the population is going to experience variation within their gene pool due to mutation and natural selection. But that mutation is the big reason for the variation, and that natural selection acts on that variation. And remember, Darwin, that's the thing he didn't know. He knew variation existed, but he didn't have a good theory for what was causing the variations. Okay, so there's a couple of different lines of evidence that scientists point to kind of show how mutations can happen and then accumulate in populations. One experiment that was done is that the scientists took some different lines of the E. coli bacterium, and they grew them in the laboratory for 20,000 generations, which sounds like a lot, except that remember that they can double their population every like 20 minutes, so it didn't take as long as you would think. And then every 5,000 generations, they took the individuals within the population and sequenced their genes, and were able to tell like whether mutations had occurred or not, as compared to the original starting population. And whoops, when you chart that out, you see something like this. So at 0 time, of course, over here, there were no mutations yet because this is the original population. But, you know, after 5,000 generations, this was the number of mutations, 10,000. Okay, there's my timer telling me that I'm just about up. So let me finish, and then so on. So it seems like there was a pretty constant rate of mutation in the population over time. And what they've found since then is that all populations, not just bacterial populations, tend to experience a similar accumulation of mutations over time, but they don't all obviously occur this quickly. So the rate differs, but we do see within all populations that over time we see an accumulation of mutations. And the idea is that these mutations provide, as I was saying, like provide the variation. Natural selection acts on the variation, and so they say that mutations are the raw material for evolution. Okay, so as you can tell from the timer, that's all we have time for today, and we'll just kind of keep going. And your at-home work is just, like I said, to keep working away at your on the origin of species. All right, y'all have a great day, and I'll be back again tomorrow.